Good afternoon, everyone, and a very warm welcome to today's technical webinar, part of the Energy Institute's technical webinar series. My name is Chim Kamwela from the hydrogen team here at the Energy Institute, and I am an energy transition technical officer and your host for today. And on screen is my contact email for anyone interested to learn more, just right after the session. So it's fantastic to see many of you joining from all over. Thank you for spending the afternoon with us. Today, we'll be talking about a key topic in the hydrogen space, repurposing existing equipment for hydrogen duty. So it's short, it's focused, and it's full of useful insights. But before we dive in, just let me go through some quick housekeeping notes. Please, next slide, please. So first things first, the webinar is being recorded, and we will share the recording afterwards. Everyone apart from the speakers will be muted, just to keep the sound nice and clear. And if you would like to ask a question, please, and we do want as many questions as well, please do pop it in the Q&A box, not the chat, just so that we do not miss anything during the discussion. But by all means, do make use of the chat itself to introduce yourself and tell us where you're joining from. It's always great to see a mix of countries and different organizations here. Okay, so let me just quickly introduce who we are as the Energy Institute. Next slide, please. So for anyone that's new to us, the Energy Institute, or the EI for short, is a professional membership body and charity for people working across the energy world. We've been around for over 100 years, and today we connect more than 20,000 professionals and 200 companies in over 120 countries. So our purpose is simple: to bring people and knowledge together to create a better energy future. So we also award professional titles like Chartered Engineer, Chartered Environmentalist, and Chartered Energy Manager. So professional standards and learnings are a big part of what we do. Next slide, please. So as you see here, we do everything we do fits into three main roles. First, attracting and developing talent. We make sure we have a skilled, diverse workforce for the future. Second, bringing together expertise and evidence to help shape smarter energy decisions. And third, helping industry operate safely, efficiently, and with lower carbon impact. So it's this mix that lets us connect engineers, policymakers, regulators, everyone involved under one roof. Next slide, please. One of the biggest strengths of the EI is collaboration, and the screen here shows the technical partners we do collaborate with and who endorse the work that we do. So each year we develop around 30 pieces of guidance, standards, and good practice documents that help the industry work safely and responsibly. So these are shaped directly by experts from operators to contractors to regulators, even academia. So the guidance reflects real experience, not theory. This collaborative way of working is what gives our material credibility, and it's exactly how today's hydrogen project came to life. Next slide, please. So finally, our technical and innovation program is where this all comes together, tackling real-world challenges across the energy sector. So the hydrogen program, which this work sits under, is one of our active areas amongst many, from CCUS to process safety and aviation. And this project on asset integrity and repurposing is a great example. It looks at how we can safely adapt existing infrastructure for hydrogen instead of always starting from scratch, which is a very crucial step as the energy transition accelerates. But I won't steal that thunder. Our chair will explain the background and how this work came about before handing over to TUV Ryland, who led the study. So with that, let me hand over to Ines McIver, our chair for the Hydrogen Asset Integrity Working Group. Ines, over to you.
Hi, thanks, Chim. Good afternoon, everyone. Like Chim said, my name's Ines McIver. I'm a Future of Energy Project Manager for SGN, one of the gas distribution network operators in the UK. So we've been working over the last few years with our colleagues across the kind of industry and gas network operators to develop the kind of hydrogen evidence base for to prove a kind of that a safe and feasible repurposing of the natural gas network to hydrogen can be done. So this kind of project came about, it was follow on from an initial couple of projects, phase 1 and phase 1A, which kind of phase 1 looked at the extent of the asset integrity issues and evaluated what kind of sector-specific information and data was available. Phase 1A then looked into what kind of current work ongoing both nationally and internationally could feed into this. What research was out there ongoing that could fill those gaps. So that was key in that. And then we formed the working group, and at this point probably need to give thanks to the previous chair, Bob Conder, who kind of was instrumental in the earlier projects and also setting up the working group. So what we done was basically we undertook then a tender process, reviewing kind of a number of technical and technical submissions that we had from various companies, and TUV Rhineland were appointed as the contractor for the work, really based on their technical knowledge and experience in this area. That was the main reason for that. So next steps of the project, obviously TUV are going to go through a summary of the work that they've done, and we're looking to move to publication of the document at the end of Q4 in 2025. An example of the front page of the previous report is shown there on the right-hand side, and the final report will be available via the usual EI publishing site. So yeah, without further ado, I'll hand over initially to Stephen King from TUV, and they can run through the work that they've done on this. So thanks.
Thank you, Ines. Thank you, Chim. Yeah, exactly as Ines just said there, we're going to take you through a presentation this afternoon, covering in a rather condensed fashion the huge amount of work that's been put in by our multidiscipline team. So we've had process engineers, we've had mechanical engineers, metallurgists, process safety, the whole range of disciplines have had input into this work. So in terms of the agenda that we're going to go through today, we're going to start off with a bit of a project introduction, the initial concept. With projects like this, it's getting started is often the hardest point. So we will talk you through the steps that we took to get this off the ground, which was really, really crucial to allow us to get to where we are today. An overview of the management of change guidance document sections and the challenges that we faced, external influences which may actually affect the longevity of the document. So we do see this document ultimately as being a live document. It's something that as more things come to light, we will be able to add to this as well. And then finally, we welcome any questions at the end as well. So I will hand over now to Scott Jobson, who's going to talk you through some of the initial stages of the project.
Good afternoon, everyone. The original scope given by the Energy Institute was for the management of change guidance document to cover transmission systems over 7 bar and up to gas concentrations up to 100% hydrogen, steel distribution systems with the design pressures between 2 and 7 bar, and any key components required to operate the system safely and effectively. The simplified graphic shows the areas which needed to be included and covered by the guidance document. One of the main issues faced by TUV was knowing how and where to start such a diverse project. One of the main problems was the limited availability of existing reference information. Obviously, this is an evolving subject to repurpose something for hydrogen duty. Go to established codes such as ASME 3112 are considered to be outdated and overly conservative for the purpose of repurposing. Previous gaps identified by the Energy Institute, such as reports 1 and 1A, are still being investigated, and the workings and outcomes were still to be published. Next slide. So the team was made up of a range of subject specialists who also had their own viewpoint on how the project should be executed and approached. After several lengthy meetings, it was eventually agreed that to treat the task as a hypothetical natural gas transmission and distribution network to be repurposed for hydrogen. And what we also done was apply our TUV hazard methodology to provide a task structure to help make sure that nothing was overlooked. Next slide. So obviously the graphic shows, the slide shows obviously the inputs which were generated into the project as a result of carrying out this HAZOP study. So it was a series of hypothetical workshops carried out by the TUV team, just as a real HAZOP study would be done with any client. The generic HAZOP actions were assigned to the TUV subject specialists, and these actions were used to help derive the content and structure of the new Energy Institute Management and Change Guidance document. So the outputs to the right-hand side of the slide show the high-level document structure. The TUV HAZOP inputs covered areas such as project overview, scope and boundaries, legal permits, environmental planning, COMA issues, learnings from experience. Obviously, as anybody knows, a lot of this publications and regulations normally on the back end of any failings or any disasters in the field. So we've done work looking into previous incidents involving hydrogen, and also hazards due to location were considered in terms of your surrounding, your neighbours, hazards to health, hazards to the environment, emergency response capability. Obviously, that's going to change with the difference in duty, and obviously any applicable standard codes and guidelines. I mean, further studies that were required. This was not a case of just referencing existing codes. It was a case of looking at ongoing similar research, development projects. Another challenges faced was different codes from different areas of the world having conflicting maximum thresholds and permitted limits. I'll just hand you back to Stephen to talk about some of the process engineering issues.
Thank you, Scott. Yeah, so I'm actually a process engineer by background, so I looked into a lot of the sort of process engineering design implications, and we'll touch a little bit on some of the safety considerations, but we'll have a dedicated section to process safety as well. So the first issue that you're thinking about for process engineering in order to sort of set your parameters is, I mean, the first issue is obviously the lower calorific value. Hydrogen has a significantly lower energy content per unit volume, volume being the key point there. There's transmission challenges, so that higher volumetric flow rate that you need to get through the pipework to meet those energy demands. There is a little bit of a case study of some example calculations that we did in a few slides' time. So obviously to get the same calorific or the same duty that you would from natural gas, you're going to need to put a lot more volume flow of hydrogen through that pipework to meet those challenges. This impacts obviously on velocity limits, and again, we'll touch on that in a few slides' time, but those maximum allowable gas velocities may then be exceeded. So you might be sort of pushing the design thresholds if you want to achieve, the same output as you would have for natural gas through the pipework. Pressure relief streams. So obviously there's wider gas dispersion zones when we are actually relieving due to the changing nature of hydrogen relative to natural gas. Increased risk of static discharge, and obviously potential there for self-ignition as well. And also when we're thinking about relief and flare, all of those existing relief devices and those flare systems and header systems need to be validated in terms of size and capacity, because there is a change process there as well. Increased explosion risk. So hydrogen has a flame speed much higher than methane. So at 18 to 59 volume percent concentrations, it can detonate. That can cause way more severe blasts than you would have for natural gas equivalent. And also easy ignition. Hydrogen's minimum ignition energy is a lot lower than methane, making leaks more prone to ignition as well. So you've got to be thinking about those control of ignition sources potentially more rigorously than you would. And lastly, invisible flame. So hydrogen burns with a nearly invisible flame in daylight, complicating leak detection and fire response as well. So we did some within the process team, we did some pretty high level calculations just to kind of get a feel for, what would change in terms of the flow rates and the velocities, mass flow rates, volume flow rates, what could we accept and what couldn't we accept. So we started with a base case of 100% methane through a 10-inch pipe, 70 bar gauge, 15 degrees. We chose a nominal velocity of 8 meters a second. I wouldn't read too much into that. I mean, that is a little bit low for potentially what you would have for gas. It is consistent with some designs that we had seen, but for natural gas, we have seen them pushing up towards that 20 meters a second as well. But it gave us a base to compare against. We then said, okay, if we want exactly the same duty out of this pipeline for methane, we'll see what we would do for hydrogen in terms of how much flow we would need through that pipework to get the same heat release. We then looked at the different blends. So we looked at exactly the same calculation, but for 20 volume% hydrogen in methane, and similarly for 10 volume% hydrogen in methane as well. So the key parameters that we're looking at, first one, velocity limits. So ASME B3112 provides guidance on what's called erosional velocity limits. Now, this erosional velocity, not a new concept to me. As a process engineer, I previously was thinking about erosional velocity in terms of two-phase flow. But there is an erosional velocity limit in this guidance document specifically for hydrogen service, and it's used to limit turbulence, vibration, internal pipe erosion, those sorts of things. Volume flow, so the hydrogen density relative to methane is a lot lower, causes an increase in the volumetric flow requirement to match that calorific duty, as I talked about before. So then naturally that drives up your gas velocity. You're driving up your gas velocity, you're increasing your frictional losses. You're getting a lot more pressure losses there. So higher flow rates in an existing pipeline, you're going to increase your friction, you're going to increase your pressure losses. We do have our proprietary software PAL that we use to estimate those pressure drops. And then we were comparing to those erosional velocity limits and those standard velocity limits that you will get from standards such as NORSOC and API 14E as well. And what happens if you have a lot more frictional losses? You need to put more compression power in to achieve that same volumetric flow rate as well. So then you're having to think about, do we have the right compression power to achieve this? So just a little summary of some of the calculations that we did. So we can see the first column there, natural gas is our base case. And then we have hydrogen exactly the same. Then we have that 20 volume% and 10 volume% mixture. You can see the compression power is the one that stands out. But also we have an increased velocity there, increase from 8 meters a second up to 30. Now, if that design, for example, for natural gas was somewhere higher, let's say 20 or whatever it would happen to be, so you get a greater mass, that 30 meters a second for hydrogen could well exceed that erosional velocity limit. But this is just sort of emphasizing more the direction than anything else. For your volume mixtures, you've got the 20 volume% and 10 volume%, which is looking a lot healthier. Your velocity limits aren't going up too much. Obviously, you do get that increased frictional loss relative to just methane. So you will get that increased relative compression power as well. So no matter what, you're going to have to put some more compression power in. I guess the question is the equipment up to the task? Just a little graphic here to outline exactly what we've just talked about there. So we have 100% hydrogen up at 30 meters a second, and the drop then, as soon as you go to blends, is significant in terms of those velocities through your pipe work. And this will be a common theme as we go through the slides as well, looking across that 10%, 20%, 100% hydrogen. I'll hand you over to my colleague Ali now, who's going to talk you through some of the metallurgical implications of the change to hydrogen.
Hi everyone. We reviewed two major databases of hydrogen incidents and found no record involving high pressure hydrogen transported through natural gas pipeline. This is good, but it doesn't mean there's no risk. So we looked at incidents from other hydrogen systems to learn what we could. As shown in pie charts, materials and manufacturing errors are the second most common cause of incidents. From this, we can draw three key lessons: the importance of material compatibility, need for advanced leak detection, and training and need for proper training. Material degradation happens across all industries, but when hydrogen is present in a system, one particular mechanism becomes much more likely and concerning. It's called hydrogen embrittlement. In this process, atomic hydrogen can diffuse into materials, especially steels and high-strength steel, and interact with defects in a way that are both known and not fully understood. This can lead to embrittlement, cracking, and ultimately failure. Hydrogen embrittlement is just one of several degradation mechanisms related to hydrogen. It is important to remember that no material is completely immune to hydrogen, That's why we must carefully assess material suitability when designing hydrogen systems. Here is a summary of material consideration. In left side, there are those materials are not recommended for hydrogen duty, and the other column is safe material. Again, there is a ongoing R&D work which may directly impact this list. So it's need a case-by-case assessment for each system. These are main steps for assessing material suitability for transporting hydrogen through natural gas pipeline. Each step is fully covered in the main document, but shortly. First, it needs to review material certificates, assess weld and fabrication history, and check compatibility with standards like ASME B31. The next is evaluating non-metallic material, check seals, gaskets, coatings, etc. The next step, conduct NDT and review corrosion history. Use NDT testing to detect flaws and review any past corrosion issues. And finally, need to consider fracture mechanism assessment, perform a fracture mechanism analysis to determine critical defect size and assess the risk of failure. That's
Yeah, so now we're going to take a look at some of the process safety implications. I'll hand over to our colleague Louise Carter, who's going to take us through this section.
Good afternoon, everybody. So this table it's an extremely high level project screening that was carried out for when we're repurposing any existing equipment on hydrogen duty. As you can see, it's less than 10% hydrogen in natural gas, less than 20% or greater than 20%, and it's quite evident that, you know, from the EC&I and rotating mechanical equipment and static mechanical equipment, there isn't a great deal of difficulty making that change until it's above 20% hydrogen in natural gas. However, on the operational management and the design kind of side, we do need to make some extra considerations, reviewing procedures, emergency and operating procedures, training and competence, inspection and preventative maintenance, as Ali's just mentioned on the mechanical side. And Steve already mentioned about release stream philosophies would need to be reviewed. So for hydrogen, greater than 20%, a full review of these installations is likely to involve some capital investment to fund some asset upgrades. Next slide, please. So first up is the environmental risk assessment, and we've put this into kind of a SWOT analysis, opportunities and challenges. So hydrogen, I think one of the main benefits is that the combustion products is just water. So this enables the decarbonisation of heating, power and industrial sectors. Emissions are reduced from the existing infrastructure. And one of the key opportunities is reusing the natural gas pipelines for this clean energy distribution. Well, that does come at some cost. As Ali's mentioned, you know, it may not be effective to use infrastructure that we already have due to hydrogen. The particle size is very small, so it can get out of any leak. We've got quite a bit of aging infrastructure. And that leak of hydrogen can be an indirect greenhouse gas. And the bottom circle on that key challenges is the global warming potential. So this actually makes it look like it's worse than natural gas. It's not. This is in terms of carbon dioxide. So hydrogen has got 11 times the carbon dioxide global warming potential. and just want to compare this with natural gas, which is about 28 times. So it's better, but it's still got that global warming potential. Next slide, please. So societal considerations. So we've already mentioned, infrastructure readiness. Public perception is quite a big one. We've got some people are very vocal, particularly on media. We've got that output, and if we ever look on LinkedIn, there's people on both sides of that position. And there's some misconceptions that may slow down this adaptation. And the environmental reality is that, grey hydrogen in particular generates CO2, which is not what we want. We also look at workforce transition into this hydrogen technology. We might need some additional roles, additional training. And then on a kind of slightly more global scale, if we're looking at hydrogen production, it's going to compete with other renewables, and that's going to have to be weighed up. Evolving frameworks are creating some uncertainty because everybody's waiting to hedge the bets to see which way to jump. And there's also a research and development lag. So there's ongoing work on hydrogen using existing infrastructure, but it is ongoing. Next slide, please. I think this is the key one. I know management of change is something everybody's really trying to get a lot better at. And it's very important. So on the right hand side there, we've got the process safety onion. It doesn't look a great deal like an onion on this slide, I will admit. And each layer of that onion is an increased level of protection or layer of protection. And we want those to all act together to produce the safest plant that we can. So we have good process design, we have plant control systems, we have critical alarm and response to those alarms. We have safety systems, relief devices, fire and gas systems, and plant and community emergency responses if the worst does happen. And hydrogen has some particular areas on there. So the key principles are we need those areas those layers to overlap, providing backup. We need life cycle integration, so all the way from hazard study 1s on feasibility, hazard study 3s on detailed design, commissioning hazard studies, and then operational hazard studies. So that hopefully kind of makes that whole area much more safe. Next slide, please, Steve. A little bit on area classification. So the Energy Institute have recently released the 5th edition of EI15, which is all about area classification. So equipment design for natural gas, which is a gas group 2A, might not be appropriate for hydrogen, which is a gas group 2C, due to its hydrogen's minimum ignition energy being significantly lower. The size of the zoning from hydrogen will depend upon the gas mixture that's being used, less than 10%, greater than 20%, all the way up to 100%. And we have seen from that EI15 guidance that at higher pressures, we can have some incredible zones created that may not be feasible to work with. At lower pressures, we tend to see that there's 10 to 20% of hydrogen in natural gas isn't necessarily significant, but anything more than that becomes a little bit more difficult to work with, and we might need to rethink our strategy on those zonings. Slide, please. And in terms of operations, some other areas that might need to be looked at. Again, we talked about mechanical reliability and integrity. Is there any additional approvals that might need to be put into that chain, management of change? And the current competency of experience working with hydrogen rather than just natural gas may suggest that we need some additional training. and keeping up records and procedural reviews. Part of that would be to reassess any zoned areas when we're using hydrogen mixes. Thank you.
Next slide. Right, in terms of asset integrity, obviously, for those who are familiar, this is a typical bathtub curve, which represents the life cycle of any normal bit of equipment. You know, from new piece of equipment installed and commissioned, it's expected that a significant amount of time will be spent snagging, tuning, or firefighting simple little teething problems shown in yellow. And after this initial period, you would expect the green segment, which is obviously the majority of the asset's useful life. I mean, the number of interventions that will be required at this point should be just for routine maintenance activities, such as routine inspections or fabric maintenance, for example. And then as normally as the asset reaches its end of its life towards the red segment, things begin to wear out or corrode, or spares become obsolete. The number of interventions obviously going to rise, and in most cases, this is the justification for investment or for a new replacement asset or bit of equipment. Next slide. What we've actually dealing with in the case of this project is a hybrid version of this bathtub curve. That's how we're trying to demonstrate it graphically. So we've obviously got the complexity of taking existing aged assets, in some cases being on the bottom of the seabed since the 1960s. And obviously this will review its original design intent, fabrication code, quality control documentation, and any previous in-service inspection or maintenance reports, and then determine its current position in its life cycle. Whether that's, we obviously, for the purpose of this demonstration, we've shown it to be at the midpoint of its life cycle. The reality of what I've just described is probably 3/4, and in some cases possibly reaching its end of life. So obviously this is how important it is to do that initial review and on a case-by-case basis. Next slide. So just moving on from that hybrid bathtub curve, this detailed slide showed the main differences between the pipeline's original design intent compared to its new repurposed life. Obviously, the left-hand side shows the original design intent considerations on natural gas duty, and the right-hand side shows the new considerations and additional degradation modes which will be introduced when changing to the hydrogen duty. And it's obviously important that any existing defects are fully understood and monitored during any future inspections. I mean, a review of the system's original installation design parameters, previous service operating condition, maintenance or repair activities, and a comprehensive inspection needs to be carried out to determine its exact current life cycle position. And obviously, from that, all these findings will then be fed into a fitness for service assessment, and ultimately fed through the risk-based inspection process, to derive a suitable written scheme of examination for any future routine inspections. Next slide. So just to summarize some of the points there, the diagram highlights, gives an overview of the potential restrictions introduced by hydrogen duty. Basically, the higher the hydrogen concentration and the increased pressure, which could be involved to get the increased volumes to the end user, the increased likelihood of hydrogen embrittlement or advancement of existing defects. My colleague Bill will now discuss some of the instrumentation aspects associated with the change to hydrogen. Excellent. Bill here is not there. Do you want to deputise?
Yeah, I think I'm back. Can you hear me, Scott?
I can hear you.
Okay. So, my name's Bill here. My background is instrumentation, and I looked at some of the high-level preliminary discussions when looking at existing equipment during a proposed repurposing of the pipeline. So on some baseline, I looked at pressure ranges, 75 to 100 bar, and velocities of 5 to 20 meters per second. the criteria I used was less than 10% hydrogen in gas, less than 20% hydrogen in national gas, and more than 20% hydrogen in national gas and natural gas. So, as was previously mentioned, when it comes to hazardous area classification, with less than 10% hydrogen blend, there's really no significant change. However, as you move into a 20% blend, you're looking at potentially up to 0.5 meter increase in, say, a zone 2 area, or maybe the zone 1 area around vents. The significant part is once you get above 20% blend, you're potentially looking at up to a 5 meter increase in the extent of the hazardous area zones, which could be significant in terms of additional instrumentation and recertification of instrumentation which previously may have been in a safe area. The gas group rating, less than 10%, I think it's pragmatic to say that 2A is perfectly acceptable. Also with 20%, the gas group rating could be 2A, perfectly acceptable, minimal risk. However, once you talk about a blend of greater than 20% hydrogen, then you will have to move to a gas group rating of 2C, which once again could mean significant replacement of the existing installed base of instrumentation. Another key aspect of instrumentation would be gas leak detection. Two of the typical sensor technologies used with natural gas is traditional catalytic, and in reality, this existing instrumentation, for less than 10%, there'll be no significant change. Once you get to a 20% blend for catalytic leak detection, there might be a small error, but it will read higher on the LEL, so it's on the safe side. So this would be acceptable generally. However, above 20%, recalibration would be required, but generally the existing instrumentation base would be acceptable with minimal replacement required. However, when it comes to existing leak detection using IR detection and IR technology, IR itself, infrared technology, will not detect hydrogen. However, if you've got a blend of less than 10%, 90% of that is going to be natural gas. So in fact, the sensor will still detect a gas leak, but it will not be detecting the hydrogen. Once you get less than 20% blend, so you move from the less than 10% to less than 20% criteria, then IR technology for the upgraded equipment is certainly not recommended, and above 20% not recommended. So the key learning point there is IR technology does not detect hydrogen. Another key topic with regard to instrumentation is fiscal metering. Some of the existing instrumentation base would include a mixture of ultrasonic technology, turbine wheel instrumentation, and good old orifice plates. And in principle, less than 10% hydrogen blend, ultrasonic is fine up to 20 meters per second. Why is velocity important? It's because generally when it comes to hydrogen blends, it may well be that to get the same sort of energy movement, then you will need to increase the velocity speeds. For 20% blend with ultrasonic, once again, it's okay up to about 20 meters per second. Once you get above 20% hydrogen blend with ultrasonic metering instrumentation, you need recalibration and seek vendor validation. For metering instrumentation, for example, turbine wheel, once again, it's okay up to 10 meters per second, less than 20%. Also, for less than 20% hydrogen blend, it's okay up to about 10 meters per second. Anything above 20%, you're looking at recalibrating your existing turbine wheels and may not be suitable if you require higher velocity transfer speeds. Orifice plate, this is generally okay, up to 20 meters per second for all blends, but above 20%, you're probably going to have to recalibrate. So that was a quick overview of existing instrumentation as potentially you change the blend from 100%. That's me done.
All right, next slide. As Stephen mentioned earlier, obviously we've acknowledged that this is a live, evolving subject topic, and obviously there's a lot of external factors beyond our control that we've had to acknowledge, and we've done that within the document by creating what placeholders. So where, for example, there's external influence which would impact it, such as global directives, obviously is the Paris Agreement, which everyone will be familiar with. But in parallel to that, there's ongoing R&D programs being investigated from materials point of view, obviously with the goal to pushing beyond the current guidance, permitted limits and thresholds. Obviously, we mentioned earlier about ASME 3112 potentially being considered to be overly conservative and out of date. It obviously doesn't suit the purpose of what we're trying to do. And obviously, there's trials such as repurposing old natural gas equipment that have been out in the field and obviously making a more realistic trial to give a more desirable outcome and a more realistic outcome. And also from a non-destructive testing point of view, the sensitivity or the existing intelligent pigs for doing internal pipeline inspections would need to probably have better understanding of the asset's current condition in terms of size and defects, and ascertain material hardnesses and any deformation to pipework, so that can be fed into the fitness for service assessments. And also one of the big factors that seems to be appearing on a lot of the hydrogen topics is obviously the training and requirement of upskilling of existing personnel to tell them and teach them how to deal safely with the dangers of hydrogen as well. So that is it.
Yeah, and that brings us to the end of the presentation there. Thank you very much. Scott, should we have a look at some of the questions on there?
Hello, Stephen. I'm just thinking, just so like the interactive element, if I should read out the question from the Q&A function. So we've got one from the EA, which hopefully all the presenters can see as well, which says, did you look into changes required on air emissions monitoring techniques for NOx, etc.? If so, are there any issues identified, for example, with additional H2O in the emission CF for natural gas?
So the quick answer to that is that wouldn't necessarily be in the scope of what we were looking at here. This was very much about the existing infrastructure, more looking at the hardware, I would say, rather than looking at different monitoring techniques or anything like that. But you're absolutely right, Jane. It's something that would need addressing. I'm sure there's ongoing work in that area from the Energy Institute as well.
Thanks for that answer. The next question we have says from John. It says, he doesn't say his company, but that's okay. It says, you described the residual life of the existing equipment as approximately 3/4 of the way through the mainstream. Does that include the PE pipes replaced under the ongoing 30-year replacement program?
No, in a straight answer. Basically, it was predominantly talking about subsea steel pipelines and low strength alloy and high strength alloy pipelines.
Okay, brilliant. By the way, for those online, please continue to put questions in the Q&A function. So the next one is from Robert. He says, how would you propose to confirm the mechanical integrity of assets such as regulators or meters for hydrogen natural gas blends? Would you recommend a fracture mechanics assessment, as typical pressure testing in water/air might not be sufficient due to hydrogen embrittlement?
Look at those. I think you'd have to have some aspect of mechanical testing somewhere in the system, and I think what you'd probably need to do is get the actual manufacturers to investigate their own equipment in order to let you know whether they have any information on that. If they don't have any, then you'd have to instigate that to proceed.
And from a meter point of view, Bill, have you got any comment on this?
Nothing to add, really.
That's fair enough. We had another question here saying, did molecular properties spectrometer MPS detectors come up in your review gas detection?
Bill, is that one for you again, mate?
Yeah, so of course there's a lot of different technologies used in gas detection. What we have tried to do is give a fairly high level overview of existing equipment that can potentially be used again as part of the overall management of change. For very specific applications, you will definitely get competent vendors involved. So for a specific requirement, then working with existing instrument OEMs, you will produce, of course, your normal specification, and that is how you would produce the required data sheet instrument and decide is it suitable for your application. But it would require some fairly detailed discussions with competent vendors.
Thank you for that. We have another question that says, how do failure mechanisms in hydrogen systems differ from hydrocarbon systems, and what implications does this have for inspection and maintenance intervals?
Yeah, well, to answer that, I've got to say that hydrogen is hydrogen, whether it's in a hydrocarbon system or in handling hydrogen pure or gas mixtures as well. The thing that people have to understand is that it's only atomic hydrogen which has the main effect on providing hydrogen embrittlement problems. So in order to evaluate that, you would have to see whether that's a likelihood for your particular application. The inspection intervals, I think, will almost certainly change, and maybe some of the locations might change, and some of the techniques could change as well. So it hasn't been a real study part of this. This is just speaking from our own TUV experience and working with both places which deal with hydrogen on its own and deal with hydrocarbon and gas processing where there's some hydrogen involved, and refineries as well. On refineries, of course, you have the added effects of water and sulfur containing material, which enhances the acidity of some of the systems and that produces atomic hydrogen in quite reasonable, specific quantities, which you need to be aware of. And in the refinery industry, they are aware of it, and they're a source of information which can help people who are not sure about it.
I suppose on the front end of that, Bob, as well, is getting a better understanding of the asset's current condition in terms of their inspection, doing that, that's how to determine where it is in that position on the life cycle bathtub curve. And obviously we need to quantify any existing defect size. Perhaps in some instances, the welding control may not be as rigorous as it would be for a new, as specifically designed installation for hydrogen duty. And also material hardnesses are critical as well for us to establish as well. That being weld caps, has zones, and obviously parent materials.
I think if you stated, Scott, as you started off on this presentation, is that you need to know what you're dealing with from the outset. So all the information you need historically on inspection, material certificates, any materials properties, everything like that, you need to have to your hand in order to find whether it's worth you carrying on or whether it's going to need some modifications essential to it for safety reasons and for a long life, and continue on the bottom end of your bathtub rather than accelerate it.
We've got another question now. It says, in oil and gas facilities, usually a critical gas cloud is used to locate flammable gas detectors. Is there any critical gas cloud established through any tests for facilities handling hydrogen?
Have you got anything to add on that one around potentially dispersion modeling and things like that? And would you approach it differently for hydrogen facilities to anywhere else?
I don't think so, and I know certainly in EI15 they used fast consequence modelling for the latest edition, and I know, speaking with DNV Fast, that they've used specific hydrogen calculations and equations, and are quite confident in the results that come out of that.
Okay.
So I don't see there being any difference in
any different approach or anything like that. No. Okay.
Thanks for that. We've got a couple of questions that we're putting in the chat, but we can go to them now. So there was one question that says, with 20% H2, why could you not change the detection level lower for natural gas, e.g. 20% now, 1%? This then becomes 0.8% set point.
Bill, any thoughts on that?
I'd have to take that one offline and give it some thought.
Yeah, I would. Yeah, just to jump on that, but I would say if there are some questions here, or if there are any questions that we maybe don't answer, or that we don't get around to, or that we maybe need to take offline, we can absolutely do that. You can forward them through to the Energy Institute, who can pass them through to us, and we'll provide answers to those offline as well.
Yeah. Yes, definitely. So we've got a couple questions left, I think. So there's one here where it says, any issues with proximity distances for HP transmission lines onshore? Notable increases likely for higher percentage blends and 100% H.
Sorry, could you just repeat that one? I can't see that one on the.
Yeah, sure. It's in the chat, by the way. It's the last kind of message in the chat. It says, any issues with proximity distances for HP transmission lines onshore? Notable increases likely for higher percentage blend and 100% H.
Louise, I'm not sure if that's one.
no particular information.
Okay, no, we'll take that one offline as well. But we'll have a think about that. And we can maybe say this. It's a huge. It will be addressed in the documentation, I'm sure. But we'll take that offline and have a review.
Yeah, no worries. So I think there's just one more question that has just come in the chat, which is, let me just get that up, which is 1 ton of H2 is 11 times CO2 global warming effect. I think that's meant to say, but CO2 is 28 times. Has there been any estimate that the potential volume of leakage on hydrogen? I don't really get what that's trying to say, but.
So I think what it's talking more about fugitive emissions. So it's saying that even though I think hydrogen is 11 times lower than natural gas. The density is such that the volume would potentially be higher, and if the fugitive emissions are higher, could potentially lead to an increase in greenhouse gas potential. So I'm not sure on that, and I because of the early stages of what we're doing at the moment in terms of management of change, I would doubt at this stage whether any in-depth work has been done around the scale of the fugitive emissions from these systems. But it's definitely something, you're right, that would need looked into, absolutely, because the whole purpose of this is about reducing greenhouse gas potential and carbon dioxide. So if that is an implication, then it needs to be addressed quickly. So yeah, thank you for that.
Thank you. I don't see any more questions coming in, and we are getting up to the hour. So I can say a few words, and then maybe I'll hand over to Tim, or if any of the presenters want to say a few words. But yeah, I just want to say thank you for everyone for joining today, this webinar. I hope you found it useful. I hope you found it informative. We do have another webinar coming up on hydrogen, on separation distances, on the 12th of November. So if you haven't registered for that and you're interested, do check out the Energy Institute website. I'm just going to hand over to Chim, and then he can hand over to Steve to say any closing remarks.
Yeah, sure. So thank you so much for that presentation. That's just brilliant work done by TUV, and the report will be published hopefully by the end of Q4. So just before we close, just a quick note, we will be circulating an email as well after this session, and this will have details on how to get in touch, and it will also have the recording link. Yeah, so just like Amy mentioned, yes, we do have another. So yeah, just to have another webinar that will be scheduled for the 12th of November. It will be based on hydrogen separation distances for small-scale installations and sites. So a calculation tool will also be presented during this session, so definitely worth registering. So thank you so much for everyone else for joining, and do have a good rest of the day.
Thank you.
Thanks, Jim.
Thank you.
Thank you.
Yeah, I guess thank you everyone for joining. Thank you to the Energy Institute, and certainly thank you to all my Ryan and colleagues, especially Scott, who put an awful lot of effort into to coordinate and everything. So yeah, thanks everyone.
And I did just see a message in the chat. Yes, the recording will be sent round. It'll be edited, uploaded to the EI YouTube's page, and if you registered, you'll get an email as soon as it's on YouTube. And we can talk about like the presentations as well, the PowerPoints. Okay, thank you.
Thanks everyone.
Cheers now.
Thank you. Cheers.